No? Yeah,
Here.
there, good. Okay.
Sorry about that. Well, John Nash was certainly an amazing person. I first got to know him something more than 65 years ago when he was a young graduate student and I was an even younger undergraduate. So we saw a great deal of each other in the old Fine Hall building, especially in the Commons room, which was a marvelous place where people got together any time of day. It was a beautiful building with many interesting mathematical artworks scattered around. For example, here you see decorations with a trefoil knot and a Mobius band with a fly walking around it. The Commons room was often full of people playing games. Here I am watching a Go game between Fox and Gonchor. Here is if you look closely, you see a game of hex, or what we called it then was Nash, since as far as we knew, Nash was the first one to invent it. So the Commons room was full of games, but also of mathematical discussions. For example, of game theory. There was a strong game theory group headed by Al Tucker and also including Harold Kuhn. But Nash was interested in everything, not only in game theory. So, as one example, when he was a freshly arrived graduate student, he managed to make an appointment with Albert Einstein. And he spent a half hour or so explaining to Einstein his ideas about radiation and gravitation and friction and such. And Einstein listened carefully for a while and finally patted him on the back and told him to go learn more physics. Well, he was always intensely ambitious. He wanted to make a name for himself, so he sought out the hardest problems he could find and did his best to solve them. So from the time he got his PhD on non-cooperative game theory in 1950, for the next 9 years, he produced an amazing amount of work. So one example, in 1952, he proved a theorem which I think nobody had expected. It was typical of Nash that he invented his own problems often. So the theorem was that if you have any smooth manifold, then you could embed it in Euclidean space to have a real algebraic structure, meaning there'd be a finite set of polynomial equations which would define the surface locally, so that perhaps I can. No, wait a minute, wrong thing. So we have a surface in the Euclidean space, and there are a finite set of polynomial equations, and so that locally, in the neighborhood of any point, the surface is exactly defined by this set of polynomial equations. It's the locus of zeros, and these equations are independent so that you get locally a smooth algebraic variety. And there was no hypothesis. He started out with any compact smooth manifold. And people were sort of amazed, but as usual, his proofs were very clearly written and beautifully written, so that it was hard to disagree with it. But I think people still didn't know what to make of the result. So, for example, 6 years later, Charles Morey proved that every smooth compact manifold could be given an essentially unique real analytic structure. Well, this is an immediate corollary of Nash's theorem, because if you have an algebraic structure, it's certainly real analytic. And it was submitted 6 years later to the same journal, and nobody noticed that there was any relation. I admit that, Maury's result was just a consequence. A year later, Hans Grauert extended Maury's result to much more general manifolds, but even so, Nash was just ahead of his time, as often happened. Another example from 1954. So he was working at the RAND Corporation, and he published an internal memorandum describing ideas for building a parallel computer. I mean, describing architecture of such a computer, how it would work, how you would use it. And this was before there were any such ideas in the general public. Maybe a few specialists were worrying about such things, but there was certainly no such computer existing at the moment. I don't know what the RAND Corporation did with this. Presumably they forgot about it, but it's still a very interesting thing. The next thing is something I only learned about a few days ago. A year later, he wrote a letter to the National Security Agency describing a new kind of encryption machine. Like most of his letters, this was handwritten, so I don't know quite what they meant, or perhaps he sent a handwritten letter because he was sensitive about security and didn't want to entrust it to a secretary. I don't know, but anyway, this is a long handwritten letter in which he described this machine, and his comments about it are especially interesting. So he said, the way you can understand the security of an encryption process is by studying how long it will take to compute to solve for the key if you're given, well, let's see, I should explain. He was sort of assuming what's nowadays standard practice in describing encryption. When you're studying security issues, you assume that the enemy has complete knowledge of the machine you're using and that he has access to a lot of the output from the machine. So you're in the worst possible case where the only source of security is that he can't figure out what the key is. So the question is, what is the computational length for how many computer steps does it take to compute the key as a function of how long this key is? And here he clearly exhibited the importance, he clearly understood the importance of the difference between computation in polynomial time and computation in exponential time. This was long before the theory of computational complexity had been invented or described. And he conjectured that any decent encryption system would have the property that the length of the computation depends exponentially on the length of the key. And he conjectured that any sufficiently complicated encryption system would have this property. And he pointed out that assuming this, it should be possible to make codes which are essentially impossible to decipher, because if the computation time increases exponentially just by taking a sufficiently long key, you can make it impossible to solve for the key with any known computational device. And this last step is especially interesting. He understood that this was an important conjecture, that it was essential for understanding security of encryption systems, but he didn't expect it to be proved. He said he didn't think that he could prove it. He didn't think that anyone could prove it. Of course, it's rather vaguely stated, but still, I think this is a clear ancestor of the P versus NP problem, the Stephen Cook conjecture that if it's impossible to decide whether every NP any NP problem where given an answer, suppose you're looking for a key and you have a conjecture of what the key should be. If you can test that conjecture and solve in polynomial time, then the problem is in class NP. And the question is whether every NP problem is actually in P. If you can test a solution in polynomial time, does it follow that you can find a solution in polynomial time? And this is now realized to be a very deep problem and a very important one. But Nash was, I don't know how many years, 15 years ahead of this. Well, next thing I want to describe is his foray into classical embedding theory. So suppose you have a Riemannian manifold, so it's a manifold where you have a concept of length defined. And if you have a map, an embedding of this manifold into Euclidean space, it's called isometric if the length of any curve on the manifold is the same as the length of its image in the Euclidean space. And a classical lemma, which Gauss could have proved if you'd asked him, I think he would have found the proof, is that if you have any smooth compact surface isometrically embedded in a 3 space, then it must have some point of positive curvature. And the proof goes like this. You take your surface, maybe something like this, in 3 space, and you draw a big sphere around it. Or think of putting a big balloon around it. And then you shrink the sphere until it touches the surface. And then it's using classical differential geometry from Gauss, you could easily check that the Gaussian curvature at that point is at least as large as the Gaussian curvature of the sphere which is touching it. And therefore, it's always strictly positive. Now, there's a catch to this. I just said smooth, but what do we mean by smooth? Well, to define curvature, you need second derivatives. So this proof only works if smooth means having 2 continuous derivatives. And any reasonable person would assume that this is just a technicality. If you can't do it with 2 continuous derivatives, surely you can't do it with 1 continuous derivative. But Nash was not a reasonable person. He just charged ahead and proved that the theorem is totally false, that lemma is totally false if we only assume 1 continuous derivative. C1 means 1 continuous derivative. So the theorem, which is that any distance reducing smooth embedding of a manifold into any Euclidean space can be approximated arbitrarily closely by a C1 smooth isometric embedding. So they always exist, or more precisely, they always exist if the codimension is at least 1, but for a compact manifold, that's always satisfied. Now, this was proved by, a weaker version of this was proved by Nash in 1954, and then Nico Kuiper, 1 year later, showed how to prove the full theorem as I've stated it. And the idea of the proof is something like this. So you're starting with an embedding which is too small. So you're assuming you can embed the manifold in Euclidean space, but the lengths are too short. The image lengths are too short. So he started putting corrugations on it, putting wrinkles, making the curve, making the lengths a little bit longer. And he did this inductively, first making very big wrinkles, then smaller wrinkles, inductively until he could get arbitrarily close to the desired. All curves would have arbitrarily close to the desired length. But now the hard part is to do this in such a way that the wrinkles get flatter and flatter so that in the limit you have one continuous derivative. And nobody believed that this was possible. It looked absurd. But again, the problem was that Nash wrote out a beautifully clear proof, so you couldn't deny it. So here's one example. Suppose we take a flat torus. So we start with a square in the plane and identify opposite sides. Identify this with this, and then identify this with this. And we get a topological torus, but with a flat metric. So every point has Gaussian curvature 0. So according to the classical lemma, you can't embed this in the Euclidean 3-space, at least with two continuous derivatives. But he proved that it was possible to, Nash and Kuiper proved that it was possible with one continuous derivative. Now this was a purely theoretical, complicated argument, and for many years nobody could really see what the result looked like. But just a few years ago, a group in France were able to construct concrete realizations to actually compute what the surface looked like, and it was good enough so they could send the image to a 3D printer and print out such a surface. And with luck, I will show you what the result looks like. So, as you see here, we start with an ordinary donut-shaped surface. Then we put enormous wrinkles in it. And then through these enormous wrinkles, we put finer wrinkles. And through those, we put still finer wrinkles. So that we get wrinkles in all scale, but making them flatter and flatter as we go, so in the limit we will have a C1 smooth surface. Maybe I should run that by you again because it's a bit amazing, if I can manage. Let's see, I think I have to start over again. So there you can see it more clearly. We just started with if you like, a tractor tire with very, very rough first order corrugations, and then we superimpose finer corrugations transverse to this. And then still finer corrugations transverse to that. Let's blow it up a little. So you see that you can see the enormous corrugations, the finer ones, and then the finer ones there, and still finer ones on every scale, and the whole thing then turns out to be C1 smooth. So I understand that if you print such a thing on a 3D printer, you can run your hand over it and it feels smooth. Okay, to Now kill this. And continue. Now it's unhappy. Let's see. Okay, now the next problem that he worked on may seem similar, but it's enormously different. Perhaps his most important paper was considering not C1 isometric immersions, but CK isometric immersions, where you have K derivatives, and K can be arbitrarily large. So this... Pardon?
Embeddings or immersions?
Embeddings.
Embeddings.
Yeah. So these successive approximation techniques that he used in the C1 case don't apply at all anymore. What you have is an essential problem in partial differential equations of a very complicated type, a system of many partial differential equations which are closely interrelated, and it was not something that was amenable to known techniques at the time. He had to invent his own methods to deal with it. So this is his theorem. Any CK differentiable manifold with K is at least 3 can be CK differentiably embedded, isometrically embedded in Euclidean space, provided the dimension is large enough. And he gave specific estimates. And so the proof was long and complicated. He had to, first of all, make a detailed study of calculus and Frechet space. Frechet space is a kind of generalization of a Banach space, which is less easy to handle, but needed for such problems. And a typical problem in working with such spaces is you keep losing derivatives. Every time you do something interesting, it becomes less differentiable. And so you need to put in smoothing operators to regain the derivatives you've lost. And it's all a very delicate dance, putting it all together. But he succeeded. And as he noticed, that this is just one explicit example of how this can be used, but he realized that the technique was important for, well, differential equations are important in all sorts of, in mathematics, physics, in many different places, and new techniques for solving more general equations can be very important. So, for example, just one step in the proof was extracted by Jürgen Moser 10 years later and used to study a quite different problem, studying periodic orbits in celestial mechanics. And the resulting, the part that he extracted and developed more generally is now called the Nashmoser inverse function theorem. It's a basic tool in such detailed studies, but it's not at all easy to, it's not even easy to state, much less to prove or to apply. But it does things you can't do otherwise. So when Richard Hamilton wrote out a detailed explanation, it took him 150 pages to just explain how this works. So you see, Nash was charging in all directions at once. He was interested in many different things, but he had a deep wish to really prove himself by proving difficult and important theorems. So at this period in the late 50s, he was bouncing back and forth between the Institute for Advanced Study in Princeton and the Courant Institute in New York. When he was in Courant, he was talking about partial differential equations and fluid mechanics, working with people like Louis Nierenberg and Peter Lax. When he was in Princeton, he was thinking about number theory, trying to prove the Riemann hypothesis, talking with people like Atle Selberg. And also in Princeton, he was arguing with physicists about the foundations of quantum mechanics. apparently he had I say arguing, he apparently had an argument with Oppenheimer which was so heated that he felt later that he had to write Oppenheimer a written apology for being so rude. Well, so he was charging ahead, full speed ahead in all directions, and somehow it was just too much. So early in 1959, he just went into a collapse. Many years later, I always thought that the collapse was caused by the fact that that the differential equations were just too hard. I've always had a terrific fear of partial differential equations, but no, that wasn't his problem. As he described it later, it was quantum mechanics that really got to him. Now, of course, quantum mechanics is also a pretty fearful subject and impossible to understand. As the saying goes, if you think you understand quantum mechanics, then you don't understand quantum mechanics. But whatever the cause was, he went into a decline for many years. He did manage to still publish a few important papers on differential equations in the next few years, but it was a very difficult time. He was frequently spent time in mental hospitals, and all in all, there was 30 miserable years after that. And all of his friends were very happy about 20 years ago when he began to pull himself together again and to make sense. And it was wonderful that this happened in time for him to win a Nobel Prize in '94. So he received the Nobel Prize from the King of Sweden, and this year he received the Abel Prize from the King of Norway. So after all these years, he at least finally realized that his work was really appreciated. And I should note that this dual achievement, one of the highest prizes in economics and in mathematics, is totally unique. Nobody's ever done this before, getting both a Nobel and Abel Prize, and I think it's very unlikely that it will happen again for a very long time. So anyway, it's a marvelous story, complicated, sad, exciting. It's life. That's the end.
Otherwise, I want to announce that we have bus outside and people with cars. So please drive up to the gate on the right-hand side here for those who don't have to join them. And we should be proceeding for the reception in the 3 minutes. Guys, do you have any other?